Hello, everyone, and welcome to our event this morning. My name is Mike Goitzman. I'm the founder of the Mobile Robot Guide and an editor for WTWH Media, and I'm going to be your moderator today. We're continuing our ongoing educational series into the technologies that support mobile robotics. But before we get started, I have a few housekeeping items that I'd like to cover. First of all, this session will be recorded, and the recording will be available after the session for viewing at therobotreport.com. If you're rewatching a session, just use the same login information that you used today to watch any session on demand. Now, the slides for this session can be found in your screen's attendee resources window, and you can download a copy to your computer. You can also personalize your experience by adjusting the webinar's window size. You can move the widgets around on the On24 control panel. And at the end of the presentation, we'll have a Q&A period. So please use the designated Q&A widget to submit your questions to the presenters. And finally, if you have any technical difficulties, try refreshing your browser window first. This typically solves 99% of the technical issues. Otherwise, you can always access our webinar producer by clicking on the Help widget. And don't forget, we've got you covered with all the latest news, information, and education about robotics with our portfolio of sites that include the Robot Report, Mobile Robot Guide, Robotic Business Review, and Collaborative Robot Trends. And don't forget about the Robot Report podcast. Now, before we get started, I want to thank our sponsor for today's session. That's RGo Robotics. And this session is going to be about taking a look at RGo's solutions. And so our featured speakers today, you're going to hear from Alon Zehngut, he's Director of Applications Engineering, and Mathieu, he's the Head of Sales. And you're going to learn more about how AI and vision systems are raising the bar for mobile robot localization systems. So welcome, Alon and Mathieu. The floor is yours.
Thank you, Mike.
Thank you. So hi, everyone. I am Mathieu, the Head of Sales Europe at RGo Robotics, and we are very, very happy to have you there today to talk about the Perception Engine and why it is the last frontier for AMR and localization in general in the robotics industry. So I will start for the first few minutes giving you an introduction, why we qualify that as the final frontier, what are the current trends and gaps when it comes to localization and navigation for mobile robots, and how does the RGo's Perception Engine bridge those gaps. And hopefully it will set the stage for Alon, so he can give you, a complete walkthrough of the Perception Engine. Alon?
Hey, thank you, Matthew. Thank you, Mike. Good morning, guys. On the second phase of this webinar, I will review deep down the product overview, tell you about the features and capabilities of RGo Perception Engine, continue to product integration, and then step-by-step deployment and demonstration of the RGo Perception Engine. Hope you enjoy it.
Thank you. So, yeah, we named that webinar the Final Frontier for AMR and robot localization. So I thought it would be interesting first to, take a step back, have a look on the current trends and technologies that we have in AMR, and try to understand a little bit better about that. As we all know, AMRs and AGVs are deployed for a long time now in various industries, but according to the latest TIC report, and by the way, I strongly advise you to read this one, very good reading. So according to the latest TIC report for mobile robotics, there are still three main inhibitors that will prevent AMRs and AGV to grow faster. The first inhibitor is the fact that most of the end users are inexperienced. So what it means when it comes to AMRs and AGVs in general is that we need to come with products that are much easier to use and much faster to deploy. The second inhibitor is the fact that most of the customers don't want to adapt their existing infrastructure to adopt robots. So again, when it comes to AMRs, it means that they need to come with a seamless integration. They need to be reliable in any kind of environment with minimum changes on it. And because it should come with minimum infrastructure, it should drive very, very low maintenance. And the last inhibitor is the customization, which is required to actually have robots that will operate in a customer's environment. And when we dig a little bit deeper into that, it's not that much the customization itself, which is an issue. It's mostly the cost of customization. So what it means is that AMR and AGVs must come with a more affordable price tag, so it will drive the shorter ROI. So now that we have that in mind, those three inhibitors, and more importantly, the 6 drivers that we can use to address those inhibitors, the ease of use, fast to deploy, seamless integration, reliability in any environment, low maintenance, and short ROI, let's see what we have when it comes to the navigation system itself. Well, today's navigation systems, obviously, they are successfully deployed and well understood, and they work in many industries as we speak. However, the feedback from customers is that they are still expensive systems, they are very challenging to integrate, and they work only in very specific environments. So out of the 6 drivers that we mentioned before to enable a faster adoption of AMRs and AGVs, we can already see that 3 of them are already falling short when it comes to today's navigation system. And let's go through those various navigation systems to see why. So the first and most common navigation system that we have on the market are obviously the 2D lidars. They are the most common because they are basically embedded in any kind of robots. They are very well understood. They can, address navigation, but also safety application. So this was the go-to system for the last few years. However, the feedback is that it's also very unreliable as soon as the environment becomes unstructured or dynamic. And on top of that, it is still a quite expensive system to have in an AMR. So those are 2 items, 2 drivers where it could improve. Other systems that we can still find on the market are the RF-based systems or ultra-wideband-based system. Those ones are fairly accurate, which is good to have for AMRs and AGVs. And the good news is that not only will it work on mobile robots, but you can also have them on any other kind of assets, should it be a forklift, a pallet mover, or even a pallet itself. However, it comes with issues as well. The first thing is that it requires heavy and expensive infrastructure, which makes them not that easy to integrate, not that fast to integrate, and it also requires quite a bit of maintenance. On top of that, when it comes to environments, it won't like environments with electromagnetic interferences. Then we have the 3D lidars, and the 3D lidars are great because they are extremely accurate. They can provide 3D data, and they will work in most lighting conditions. However, they are still extremely expensive and also very, very complex to integrate, which doesn't make them very easy to use, very fast to deploy, and very easy to integrate. It also requires a significant amount of manual work to clean the map. And even if they are very good at detecting obstacles, they are not that good at performing localization when we are in dynamic and complex environments. Which is why then, the industry tried to introduce the visual SLAM. And the visual SLAM, it kind of fits the bill. I mean, it's very reliable, even in the most dynamic environment. It's extremely cost-effective because it uses only a single 2D camera. It's very fast to integrate and to deploy because most of the commissioning is done automatically. It requires very minimum maintenance because, again, single camera, no infrastructure. And it's easy to use because, as mentioned before, Most of the commissioning is done automatically, so you don't need to be an actual expert to use the system. And the good news, well, before we go to the good news, sorry, the issues are that, first, because it's camera-based, it cannot operate in complete darkness. And until, like 2 years ago, it was difficult to integrate because it's a very data and computing intensive system. But these days, with the latest progress that we could see in computers, it's not that much an issue anymore. So if we have, a broader look on the actual navigation system landscape, and again, I took it from the STIC report, we can see that according to STIC, the Visual SLAM is really the navigation system that these days checks all of the market boxes in terms of ease of use, cost, ease of integration, maintenance, etc., etc. It's also very future-proof because it can enable obstacle detection as well, for instance. And the good news is that the perception engine from RGo is obviously based on Visual SLAM, but it's much more than your regular Visual SLAM, as Alon will show you in a minute. And before we jump into the details, I just want to, frame very quick what are the key benefits of that perception engine based on Visual SLAM. First, not like any other Visual SLAM system, it is an adaptive system and self-learning system. So it will fit and adapt automatically to any kind of environment. Second, it's very robust, very accurate. It doesn't drift like your regular SLAM system, and it will be so even in the most highly dynamic or repetitive environment. Third, the map creation, unlike with 3D LiDAR, is 100% automated. So you don't need to pay any engineer, any technician to have a clean map. And last but not least, this mapping process is continuous. The system is learning every second, and if there is any changes in the environment, it will adapt accordingly. So now that we can see a little bit better what are the benefits, I will give the mic to Alon so he can basically tell you how we do this kind of magic.
Thank you, Mathieu, for the introduction. And let's go for the solution. So again, good morning, guys. In the next 30 minutes, I will guide you through about the solution itself, how we integrate it to our customers and to the robots, and give you a demonstration how the system works. So before we start, maybe a quick brief about RGo Robotics. RGo Robotics is an American-based company based in Massachusetts, and most of the R&D are Israeli-based in Caesarea, which is a little bit northern than Tel Aviv. We are less than 50 employees, experts in computer vision algorithms and sensor fusion algorithms, combined together the most advanced technology you can find out in the market today. About the product itself, so the perception engine, what it is, it's a full stack solution. Stands for localization and perception software that is tightly coupled with a low-cost camera and reference design. It was mission specialized for wheel-based robotics, and it's been trained and learned in many applications on site, which means this perception engine and the algorithms has been deployed and run with dozens of multiple different applications and different sites to gain the knowledge and to learn how to operate best in every environment. And that stands for both indoor and outdoor environment, which is the uniqueness of the RGo Perception Engine. Then the next one, I'm going to talk to you about the product integration. So how the product looks like and how to integrate it. Standing in the hardware standpoint, we are mostly focused on two versions. The first one on the left will be the industrial enclosure version, which means that every machine or every robot can integrate the perception engine as a retrofit, basically mounted whatever it suits, as long as the camera see something. It can basically be mounted everywhere, as long as you have at minimum 20 centimeters height, but it goes all the way even to 1 meter, 2 meters height, as long as you see the floor, see the ceiling, see the sides, we're using a global shutter fisheye camera, which see almost 180 degrees field of view. So on the left is going to be the industrial closure version, and on the right is the bare board version, which basically means you can design your AMR or your robot with the RGo Perception Engine in everywhere you want. You can take the system of model, place it in a convenient way in your AMR, as long as you have enough space for the MIPI interface to the camera, and place it in a convenient place. You can see here in the camera, we have the SOM, the system of model, which is for the compute. You can see the camera module, which holds the IMU, the inertial sensors, and the global shutter 1 megapixel fisheye camera for this version. Let me give you another, explore the options of the compute. The RGo Perception Engine, as I mentioned before, is a full stack software solution, computer-based, computer vision algorithms that can run on multiple platform options. On the left, all the way for a cost-optimized reference design, can go all the way for a consumer product. So even if you're a vacuum cleaner manufacturer, such as go for iRobot, etc., or lawnmower robotics, for affordable products, the RGo Perception Engine stack and algorithm can even run on a very cost-optimized compute, which gives you roughly magnitude bill of material around 50, 60 bucks, that cheap. On the center, you can find our standard CPU and compute option. This is mostly used wider for our customers. It's a 6-core ARM 86 architecture, CPU based, and is also very relative cost effective for supporting multiple applications. On the right is the premium reference design, and we fully support the entire NVIDIA Jetson family, all the way from the Xavier for the expensive one and the Orin family. We have some customers that already has been deployed with the Orin family, utilizing all of the Perception Engine advanced capabilities, running together with their own software in order to save costs for the hardware. In that manner, you can run both the application layer and the RGo Perception Engine stack on one single compute on your platform. To give you an example how it looks like, this is one of our customer, is a Norwegian-based company, widely deployed in the States and Europe, stands for Wilmi. And you can see here on the picture on the left, that was an original wheels. They have a really nice, cool methodology of using 4 independent wheels. They can do reshaping of the robot. And you can see on the left here, this is the NVIDIA board with the RGo Perception Engine module, camera module, standing out here. Just so you can take any impressions, you can see the video of how the product looks like, which is quite cool. So you can see it's 4 and can be 8 wheels, designed for any kind of applications, go the way for manufacturer, industrial warehouse, different environment. And they have been deployed and order a lot of units for the RGo Perception Engine that is integrated inside one of the wheels, the master wheels. Another example, another great example for one of our customers is the Capra Robotics. By the way, Capra Robotics was founded by Niels. He was the CEO and founder of MIR, Mobile Industry Robotics, one of the top lead AMR manufacturers in the world. And they founded Capra, which is an intralogistics AMR. They can go both indoor and outdoor. And I think in this slide, you can see a great example of different ways to integrate RGo Perception Engine. On the left, you can see a full industrial IP65 enclosure for outdoor application here. Then on the middle, there is a traditional ROIC platform that carries on pallets and other stuffs. They also used by MIR, for example. You can see the camera just designed, mounted in the front. And here on the right, another design where they take the board and the camera, basically integrate it into the platform. Let's talk about the modules when we talk about perception engine and what the core product looks like. If you look at the left, so the basic foundation of RGo Perception Engine is based on a sensor fusion module. When it listens to the wheel encoders, this is the odometry, so what is the velocity of the robots, and then takes the images from the camera and the measurements from the IMU, gyroscope, magnetometer, and fuse them into a fuse data that eventually can tell the robot where it is in a 6 degrees of freedom, which stands for X, Y, Z, and pitch, roll, and yaw in very accurate level. Of course, there is an optional additional sensor we can integrate it, such for outdoor application. We sometimes use GNSS RTK, for example. We can also fuse it with depth sensors and LiDAR sensor for more safety and depth and obstacle detection application, etc. If you're looking about the architecture, so on the left, this is the OEM, the robot application. You can see the application layer, and this is direct speaking with the API of the perception engine. And if you look about the hardware layer, so this is going to be the camera and sensors connected to the compute, and they basically going to listen to the robot application processor that grabs the wheel encoder and send it to the perception engine. Quite basic architecture. And that will lead me to the API slide. I promise not to go too much deep, just a really high-level review about the API features and capabilities. So without going into every box of these ones, I just want to give you a really glimpse what you can achieve from the perception engine. So this API, of course, include very much different services and mapping services. So you have this software update and logging. You can inject wheel encoders and inject different sensors I mentioned before, such as LiDAR, depth camera, etc. And this is the one important one. This is the API that transmits to the robot. Of course, there's a 6 degrees of freedom position with confidence, right? There's a driving feedback. We sometimes send the robot recommendations what to do, such as turn in place, stop, or improve the maneuver in order to achieve high accuracy. We also have a high precision mode where we use sometimes a RGo or April tag or QR to get a millimeter accuracy level, which is sub-centimeter. And if we're using a depth technology such as time of flight, depth, camera, LiDAR, we also utilize and send you a free space data for the warehouse. We have another services of mapping and map management and different alerts and states and calibration and configuration, which are going to be deeply reviewed in a technical session that you're welcome to join. But this is basically the API. Now I'm going to give you a short description by step-by-step deployment and how the perception engine works. So let's talk about learning a new site or mapping, what we call site exploration. On the right, you can see an example of our RGo console, which is a web GUI for integration phase and management state for the perception engine. So the site exploration, of course, is done once, right? You arrive to a new warehouse, you explore the site, as well a vision system. We need to see everything from multi-perspective, and that way, from now on, we can operate in a very accurate way in this site. The map will be auto post-processed and ready to use in minutes. So there is no need to post-process it manually or clean all those static objects. The perception engine does it automatically and knows to identify which one of those natural features to use in its map. Then the map will be shared to the entire fleet. And I think what's most important is no need to stop any operation of the facility. The perception engine can explore the site even if the operation is continuously and the forklifts are moving and the people are moving around. There's no need to shut down the warehouse, which is very critical for ammonia applications when they want to deploy on operational site. As Mathieu mentioned before, the map is continuously been updating, and if there is movement and changing for the facility, the map will automatically update itself continuously. And as I mentioned before, it also works for indoor and outdoor. Just to give an example how it works, so let's keep it with a video in the background to be a little bit less boring to hear me bragging all the day. Just give you an example of a typical site. This is one of the testing sites we're usually working on. So it's a typical warehouse when we do a lot of accuracy tests and experiments. And as you can see, this is an example of a not structure one, right? With a lot of pallets that are keep moving all the day. This is the second level of the warehouse when you have aisles and all. And you see the people are working and doesn't stop the operation. And here you can see the easy go operation with our tablets and the UI. The operator just need to create new map, enter some info like area, size, and name, start the perception engine, and the next step, the perception engine requires you, let's just do a basic out-of-the-box calibration, which is done once per site. It will spin around basically for the IMU to measure itself and give you a very accurate performance before you go. As you can see, the mapping process will be relatively easy, just driving around using a joystick, manually driven around the warehouse. You can see there are a lot of people still working in the warehouse. You don't need to stop the operation, as I mentioned. And if you can see, the robot will travel back and forth in the aisle. It will usually try to close a loop, as a traditional SLAM system needs, to get more accurate and dense graph. And that's about it. After the perception engine will close itself, it will be ready to use within a minute. So that was site learning. How this magic works is a brilliant question that people ask me. So as a vision system, traditional vision systems sometimes look at the difference between frame to frame, try to evaluate the changes between one of the frames. But as you all know, this will accumulate error every once in a while when you drive, and the best VSLAM system will tell you there are less than 0.5% error. But when you drive a kilometer, it's a huge one. What a perception engine does, and we call it a learning vision system, it will keep learning the environment, looking for a unique descriptors and structures in the environment. So in this example, you can see the door and you see the ceiling, and it will continuously looking for hard structure you can rely on. And that's okay, because even if the next round they will move, he will know, okay, this is less strong, I can still relocalize myself on these ones and maintain a strong database of how the map looks like. Maybe let's give you an example. I know it's going to be something confusing. So this is a traditional visualization of the SLAM data sets. So if you can look in this video, this is a 3D point cloud, which represents a natural features in the environment, right? And you can see there's a complete structure of this one, and there's like thousands of descriptors that will help the perception engine in the environment to know exactly where it is in every single point of the warehouse. The next feature I'm going to review is how to align yourself to a blueprint. A lot of our customers, they have a blueprint or a CAD drawing of the facility to visualize itself. And the RGo Perception Engine can be automatically align itself to any blueprint or any representation and any other coordinate frame you got there. It's kind of basic operation when you just tell the perception engine where you are in the real world, and he will know to auto-convert itself to your coordinate frame and your map representation. Let me again demonstrate how it looks like. So again, we have this nice, cool web UI for the user, just to demonstrate how basic and simple this operation. I hope you can see the video now. So the user will just choose the map he's already explored, the map he want to align to, then goes into the menu to select the relevant blueprint. Now in the video, you see the phase when he's anchoring to the map. So for example, I learned the Shechts one. This is the map that I've created previously. I will choose this one, then I will upload the blueprint. You see, this is the blueprint of these specific aisles, just for this example. Now, the next thing I need to do is to tell my RGo Perception Engine the scale of the blueprint. As this one is a picture with pixels, we just do the translation between pixels to centimeters, meters, or feet, of course, in states. And this, the way the blueprint can get its scale. And now the next step will be just tell the perception engine where you are in the blueprint. So the operator will actually need to drive manually the robot to this specific point in the warehouse. And it's usually very simple to choose just 4 pillars or 4 poles, very standing out in the warehouse. So you can see the operator, and now he's going to be driving the robot to this specific pole or pillar. He will stop for just a second, tell the RGo Perception Engine, this is where am I at the real world. And you can see here with a very intuitive UI, easy operation. You just click the button, say, I'm here, and then continue to the next point. And the minimum required point will be 4 points to do an accurate translation. So he now will continue to additional points. And when it's done, he said, I'm done. Please create an alignment. And there you go. Now you have a nice visualization of this blueprint. And the robot, it travels, and you can see the correlation between the robot's travel down the aisle with the UI. And this is need to be done once. And again, share for the entire fleet, of course, as they use the same translation metrics. Very nice and easy, very cool. And let me maybe give you another customer example, how it looks like. Just a second, I need to stop this one. So we have one customer, one application that actually doing a teleoperated forklifts. And you can see in the video, they basically drive the forklift and they see where is the forklift on the warehouse, which is relatively easy and very cool. The next feature I want to review with you is how I measure how accurate am I, right? I learn a map and then maybe I change some things in the warehouse and I want to make sure my map is perfect and there is no accuracy, precision issues. Then we have this test wizard, very easy to use and activate. So it basically, you can just choose a waypoint, click the button, it will create a waypoint. Then every time you visit this waypoint again, you can just click the mark button and it will sample the position and give you statistics about how accurate you are. Usually for indoor environment, we say in the spec we are sub 5 centimeters precision accurate, but usually from my experience, we can achieve 1 to 2 centimeters on a very typical accurate place. For the more complex one, with very dynamic, very repetitive environment, it will be around 4 to 5 centimeters. So that's roughly the numbers. Again, just to give an example, how accurate we are and what does the robot sees comparing to different technology. So this is another demonstration about the precision of the robot. And what does it see is comparing to the LiDAR, for example. So you can see here in the video, we just choose a point, right, where the robot is. We mark it as a test 1 point. Then the robot just travel over and over to the same point, try to see if the repetitiveness of the perception engine. And you can see when we drive it manually to a specific point in the warehouse, the icon of the robot will be just on top of this mark sample point. You use these boxes just to mark this physical place. And in this video, you can see a drone footage on top view of the robot and its position. You can see on the left top the actual position on the blueprint. But I think what's most fascinating is the left top one and what actually the robot sees, right? So comparing to this system, this fisheye see really wide field of view. And you can see the sides and the ceilings and the floor. And in this test, we keep pushing more and more boxes and more elements and forklifts around this environment to give it maybe a hard time, to give it a challenge for the perception engine. But again, it works every single time. because he had so many thousands of descriptors he already captures in his environment. So even though if we move more and more and add more and more boxes, it will still localize itself in a centimeter, 2 centimeter level precision, as you can see in this nice demonstration. Right, I hope you enjoy this one. And then maybe to switch to a video, I want to give you another example of a real customer. This is the one that I told you before about a couple robotics one. Let me play this video and then talk about it. I think this is one of the nice examples of an application that goes all the way from indoor and outdoor using the same app, same perception engine. There is no RTK, no GPS in this one. There is accurate docking, right, with the ROX system. It can use the docking with the precision mode using a QR code or even with a depth. And then you're going to turn now, you can see the camera on the front. This beautiful device uses the single camera by RGo to navigate itself all the way from inside a warehouse all the way outdoor application. You're going to see it going now outside from one building to a second building. Navigate itself with a very accurate position between those environments, as you can see. And again, there's the challenges of lighting, and there's now the shadow, there's direct sunlight, and the environment condition is going to be changing continuously. But RGo developed its own AGC mechanism and its own algorithm that can handle all those environment extreme condition. We can work all the way from almost 200, sometimes even low, 100 lux, all the way to direct sunlight condition. As you can see here, it switches between a lot of environmental conditions from dark to shadow to sun, then go all the way back to indoor environment, which I think gives maybe the best practice of how the system works and how the system operates in a very interesting and complex use case and application. So this is maybe my last example. And I'm going to wrap it up with a quick summary about the perception engine. So starting off for navigation, we talked about precise 3D localization. And it's very important to mention 3D localization, and sometimes even for a warehouse, you have those trucks go outside on a ramp and you got a inkle, and sometimes those 2D navigation system can lose track. So we have a precise, robust, in-dynamic 3D localization. As Mathieu mentioned before, there is no infrastructure required. So there's no reflectors need to be mounted and no QR code on the floor. This system is natural features, learn the environment, structure its database and its map, and it can go all the way in an indoor and outdoor operation. Dynamic and unstructured environment, again, as discussed before, we are working alongside people and machines and continuously updating our inside database in order to achieve this centimeter level accurate in every condition. For the high precision mode that I mentioned, we have a built-in marker detection. This is basically used for precise docking. If you have a charging station or you have a very specific docking station you want to approach, yes, we can use one of those Aruco's QR April tag, auto-detect them, and then achieve even a sub-centimeters, a millimeter level accuracy. This is done for this one. Even the 3D obstacle detection technology and algorithms achieve a very high level of a millimeter accuracy. We didn't discuss much in this webinar. We focused on localization, but of course the perception engine facilitates all kind of perception, sophisticated layers, all the way from high human detection, object recognition and classification. That requires usually the higher compute stack for that one. And then the integration is quite simple, quite straightforward, as you always need power from the vehicle, wooden coders, and this camera is very small, relatively small, can be mounted and placed almost everywhere. Yeah, so that's about it. I think I'm done for this one. And I think we have plenty of time for a Q&A, which I'm sure will be an interesting part for this webinar.
Yeah, great. Well, thank you, Alon and Matthew. Matthew, do you want to say something before we go to Q&A?
No, I'm good. I was just saying that, yeah, we do have some questions indeed.
That's right. And so I'll remind folks once again, if you'd like to ask a question of our presenters, use your Q&A widget in your On24 console. That's where you can submit the questions. We've been queuing up quite a few here during the conversation. So while you guys are finding that Q&A widget, if you have a question to ask, we've got a few queued here. So let's start with the first one here. And this question is about updating the map continuously. I think you guys talked about a little bit about that earlier. So the question is, how is the map continuously updating? Is it updating when the AMRs operate daily as they traverse through the facility? Who wants to take that question?
So I will take these questions for sure. So maybe it's important to understand, not like other systems, the perception engine is continuously updating its database. It's not when you trigger it out. Every time in Zehngut, when it runs in the warehouse, it continuously updating its database and its 3D point visual anchor points all the time. Then, of course, there's later different AMRs also working in this environment. Then the next phase, those data can be used to merge in the cloud and then be spread out to different AMRs. But I think that the basic principles and what you need to understand is how the perception engine works. Every time when he goes, even in an aisle, and he see a forklift that was not there before, he will continuously updating his structure to more stronger and continue scoring those features in order to achieve a robust, accurate position in a very dynamic environment.
Interesting, right. And now you did talk about the fact that the system can operate both indoors and outdoors. And so here's a question about, I suppose, outdoor support, but you can expound on this. Does the system support non-GPS supported environments?
The simple answer is yes, and I think this is an example that I showed you before with the Kappa Robotics, as they didn't utilize any GPS and RTK at all. When this application uses both indoor and outdoor for a traditionally kind of basic environment, it can operate without any GPS or RTK, as you know where it travels from this feature from the buildings and signs. But of course, it's going to be application dependent. So for example, we had one application when you had to drive a big, fast machine. We didn't talk about the specs, but we also work with 5 meters per second, 6 meters per second fast vehicles. And those one, even in outdoors, will require very accurate position. In those ones, we definitely fuse a U-Blocks RTK into our system and use its confidence data with a perception engine in order to achieve more accurate and more robust data for outdoor application.
But you can run in without a GPS signal. You can still maintain your localization and know where you are.
They definitely are, and I think this is one of the nice. Both technologies are comprehensive and completing each other. While you don't have any GPS signal, it's mostly going to be because of buildings and no RF signals, and this is beautiful for a vision system, as you have more features to be relied on and to work with.
Interesting. Yeah. Well, here's another question. This individual's asking, how many depth cameras are required? You just talked about sensor fusion, so you're fusing data from a variety of different sensors. And do you use LiDAR as well? So talk about how the sensor fusion works and what kind of sensors, how many you can bring together.
Right. So maybe just to clear this out, and if it's not clear enough, for localization, accurate 3D localization, we don't use any 3D depth, any depth camera at all. We can use a single fisheye monocular camera, and this is the one we use for localization. Then, of course, for obstacle detection, we use depth cameras or time of flight or different technologies, and the number of one will be depend on the application and the field of view coverage you will need to achieve with your machine.
Interesting. So let's see. Here's another question. While you're on the sensor topic, it says, "What's the range of detection?" I guess that's dependent on the sensors, but what's your response to types of sensors to use and how far you can see and accuracy at distance? How do you talk to customers about that sort of question?
It's again a brilliant question, and again I want a differentiation between localization features and obstacle detection features. For localization, the detection range is almost infinity, is the horizon, right? The camera sees very far away and can use very far features, as we call it spatial resolution, right? As it translates those features to pixels. And again, in terms of obstacle detection, it usually depends on the additional sensors we add to the system. And then you have typical depths cameras such as the RealSense one that usually customers achieve around 3 meters with high resolution. And with the improved algorithms for RGo, you can achieve 5 to 6 meters with the same sensor.
Well, while we're talking about the camera then, and the sensor, here's a question about what's the field of view? And you talked about the monocular fisheye lens. What's the field of view for that type of camera?
So maybe I can pop up this one again, this slide.
Yeah.
Okay. Good. There you go.
Yeah, I know how to use this one, huh? There you go. I think this may be one of the brilliant facts about RGo, right? As we took and designed a camera module, and you can see this is the size of a 50-cent coin. If you go to our website, you can definitely see, and maybe I can use this one. This is a NVIDIA Orin, and this is maybe a pen. It's very small. And this camera module we designed as a reference design using a commercial off-the-shelf components. So it's going to be an OmniVision imager that is widely used. And it's going to be one global shutter camera, 1 megapixel camera. And for your question for the field of view, the maximum is going to be almost 200. But then for most of the application, we use less than that. The minimum we use is 160 degrees field of view. So you have kind of constraints for the mechanics of the platform. We still require 160, but the camera sees almost 200.
So that's interesting. When I realize you're talking about a fisheye lens, it distorts the view as we see it as humans, but there's a lot of information in that distortion that you guys are using for perception, right? As things roll past the lens, that's quite an interesting take on using that information.
Yeah.
Great. So here's a question. How does the...
Yes, and maybe just another to emphasize, Mike.
Yeah. Go ahead. What did you want to say?
Sorry, there must be delay. Because we are a very fisheye camera, even though we have an narrow aisles or pallets grabbing around us, and the field of view is going to be a little bit obstructed. Sometimes, 2D lidars, they see only a slice of the board that they will struggle with. But since we always see the floor, we see the ceiling all the way, we can always rely on those features we have in our database to localize ourselves in a very even challenging dynamics environment.
Mm-hmm. Now, here's a question someone asked. It's related to the sensor fusion, which is as you drive around and you're using the odometry from the wheels, vehicles that are equipped with mecanum wheels, for example, slip, and so the odometry of the actual wheel encoders maybe not good information, but other types of tools that give feedback as to where this center of the body is, or how it's moved, or how much it's moved, that type of thing. You talk about how you integrate with other types of devices like the encoder feedback from the wheels. Is that something you can do, or is that important?
I was a little bit difficult to hear, Mike. Maybe it's my internet. But you're asking about sensor fusion and in different wheel encoders and driving ways, right? That was the question?
Correct. Yes. I think that's the gist of it.
Yes. So to give you a grasp, our sensor fusion guy, they work almost 3 years in improving those algorithms, so they can receive any types of read encoders, all the way from the good ones and the very accurate ones to the shitty ones. And how we do it is we use all the data we can have to eliminate any faulties and any bad data. And for example, when you talk about slip, yes, those mechanos and other wheels can a little bit slips. We compare it with the camera vision and other data we have in the system in order to detect those slips, in order to detect the robot movement. That way we can give you always the best robust localization, because we don't just rely on the encoders. We use them as an additional information with a bunch of sensors that goes into our sensor fusion there.
Interesting. All right, here's a specific question about a specific AMR vendor. So this individual says that they are using a pilot project with mirror AMRs in a very dynamic environment. Have you ever integrated with a mirror to augment their localization obstacle avoidance?
We didn't work directly with mirror platforms with them, but we work closely with some of their partners in order to tackle those challenges, for sure.
I think what we can add is that even if we
Mathieu,
don't,
you want to elaborate more?
Yes, sorry, there was a bit lag. Maybe what we can add is that even if we don't work yet with Mir to have Perception Engine directly integrated into a Mir robot, first, if there is anyone at Mir in the audience, we are more than happy to discuss about that. And if we have customers that are using Mir robots and would like to retrofit them with Perception Engine to improve their performance in a dynamic environment, then obviously we can do that because we have this API that will allow us to basically communicate with any kind of robot, should it be using ROS or just a regular C++ API.
So Mathieu, maybe you can expand on what is your typical approach for a customer integration, and if someone comes to you with a new bot that you haven't worked with before, how do you take that project on?
Yeah, that's a very good question. So usually the first thing that we do when a customer wants to integrate Perception Engine into one of their robots is that we first do what we do, a pilot integration. So it's a very engineering level integration that will take only a few days to achieve, and after maximum 48 hours of integration of Perception Engine onto the robots, then our customers can run all the tests that they want for, I don't know, from 1 week to some of them go up to 3 months. And then after that, we usually have demonstrated the capabilities of Perception Engine. And then it will depend on the customer. Some of the customers want a very deep integration of Perception Engine into their existing hardware. So in that case, we'll make sure that the compute and the camera are completely baked into their existing robots. And some others, because they don't necessarily own the robots, will be more than happy to have the box, the enclosures that we've seen before, and they will just, bolt down on top of the robot, plug it to the rest of the robot, and it will be up and running with localization through Perception Engine. So really depends of the customers, but to sum up, pilot integration first, then deeper integration depending on the requirements of the customer, and then deployment. Few days for the pilot integration, a few weeks for the deep integration, and then deployments over several months most of the time.
We get another question that's somewhat related to that. So I'm gonna extend what you just said by asking, this customer is talking about adopting one of the problems about adopting AMRs is ease of use and interoperability with the users. You mentioned IoT integration. Can you integrate with, for example, IoT push buttons or trying to eliminate an iPad or to interface with users on the floor?
Yeah, I mean, I can give you an answer on this one. Maybe Alon wants to go deeper, but the iPad that we use is basically for the out of the box, and it's because it's the interface that we at RGo developed to make our customers' life easier. However, most of the AMR manufacturers and integrators with you will use Perception Engine through the API. And then you can basically, well, trigger the API through push buttons or whatever you want to make it, suitable with the actual use case of the final end user. Alon, is there anything you want to add to that?
No, I think it was a perfect answer. We mostly use the iPad just for the initial phase, integration phase. Then later on, just using the SDK and the API directly from the robot application, and then can trigger and do the whole process autonomously with the API. Everything you can control from the UI, you can use the API with.
Great. So we're getting near the end of our time here, so I'll just make one last call. If you have any other questions to ask, now's the time to get them in, or I can take maybe one or two more questions here. And again, we'll give these guys all the questions that have been asked that we don't get to, and they can get to you offline with your answers. So having said that, back to the application area, the question is, can you operate in extreme temperature environments, like into a freezer or maybe outdoors when it's really cold? What's sort of the extreme sort of conditional environments for your system?
Yeah, I can easily answer this one. The one example that I show you from Robotics, they're Denmark-based companies. It's very cold now in the winter. They operate both in outdoor and very cold environments. And even one of those use case, they're working on a slaughterhouse, going inside and outside in the refrigerator in the slaughterhouse. So we definitely utilize and test our system in very extreme cold and dynamic condition for that one.
Interesting. Wow. Yeah, that does sound like an interesting application. All right, we'll get to one last question here before we call this a day. So I guess it goes back to sort of the architecture for the system. It says, does the system need any more than a cell phone grade IMU?
Well, I can give you less than that. Our IMU is already mounted and built in within our camera module, right? The entire camera module, which is in the cost of around $20, already contains a basic IMUs. What we do in RGo is take a commercial off-the-shelf, cost-effective sensors and take the best out of them, right? So we continuously learn the error and correct it and use our own IMU. So there's no further IMU you need to buy, no fancy expensive ones. It's already been supplied with this $20 beautiful camera. Give you really beautiful results.
Great. Well, gentlemen, it's been a very informative conversation today. I want to thank you for your time and effort. I learned a lot. I hope everybody else did. So thanks for your time. Thanks for sponsoring this session. I want to remind everybody that you can learn more about RGo Robotics at RGo Robotics.ai. Go check them out on the web. And thanks to Alon and Mathieu for their time and energy today. Appreciate that so much. I know you guys are in a different time zone on the other side of the planet from me, so late in your day. So thanks, gentlemen, for that. I also want to thank our producer, Lindsay Harvey, and the rest of the WTWH webinar team for all their hard work. My name is Mike Weitzman. Thanks again, everyone, for attending.
Thank you, Mike. Thank you all.
Thank you, everyone.